So in this video, we're going to be looking at the equilibrium constant again, but this time in terms of the constant Kp. Now, so far what we've looked at is the concentration of our reactants and our products. We said products divided by reactants, that gives us our value for Kc. But in this case, right, if we're dealing with gases only, we can actually measure a value of Kp by taking the partial pressures of each of these individual gases. Now, the reason why we actually use pressures instead, and hence Kp instead, when we deal with gases is because it's easier to measure the pressure of a gas compared to the concentration. Now, when we look at P is going to stand for partial pressures when we deal with our equation, and of course our units is going to be pascals, kilopascals, atmospheres, could be anything really that's used to measure the pressure of a gas. In terms of Kp, we only include the gaseous species, so anything that's going to be a solid, liquid or aqueous, we kind of just get rid of that. Now let's say I've got this general equilibrium over here. You can see everything's going to be a gas. It's going to be a homogeneous equilibrium. If I were to write the Kp expression for this, I would have Kp being equal to, I'd have my products over reactants, so I'll have the same thing as my Kc expression, where I have C and then of course I'll have D as well, but it's going to be different in two ways. It's going to be different in the first way by having circular brackets rather than square ones. I'm going to times these both together. I'm going to have my powers just as normal before as well, but then this time I'm going to have a small p next to C and D. So I'm going to have the partial pressure of C times by the partial pressure of D. That's going to be divided by the same thing with my reactants. So I've got A squared, and that's going to be in circular brackets as well, times by B. And don't forget, I'm going to have some small p's there as well. That's the second difference that we can get. So yeah, there's my expression for Kp. Now what about the units of Kp? Because of course we're not dealing with concentration anymore. What would the units of Kp actually be? Well, let's say if I had my partial pressures in this case as being pascals, let's say if I were to have pascals for these units, all we would do is take whatever unit our partial pressure is, like pascal, kilopascal or atmospheres, and I'll just sub that in just like before. So I have pascals to the power of 3 times by pascals divided by, and then it's going to be pascals squared times by pascals itself. What happens is these like for like terms, they cancel, and what we're actually left with is something that looks like this, where our units end up being pascals for this expression of Kp. But of course we know it can change every single time. Now moving on, if we were to look at this task, I want to pause the video, have a go at the following in writing the Kp expression for A and B. Pause the video, resume once you're ready to go over the answers, and we'll go over it together. So looking at question A, you can see of course I've got N2O4 as my product, so I'm going to have Kp being equal to the partial pressure, because remember we're dealing with a homogeneous equilibrium. We've got all gases here. The partial pressure in circular brackets of my product, which is N2O4, and that's going to be divided by the partial pressure of my reactant, which is going to be NO2, and that's going to be to the power of 2 as well. Remember, you need circular brackets here as well. There's our first one done. Looking at the next one, I've got my product in this case, which is going to be ammonia. I've got 2 lots, so Kp is going to be equal to 2 lots of ammonia, 2 lots of partial pressures of ammonia. So I've got P, NH3, and then of course 2, and that's going to be divided by P, and then it's going to be N2 to the power of 1 times by P, and then it's going to be hydrogen to the power of 3 itself. And there's my Kp expression done. So yeah, moving on then, what about if we were to ask to calculate a value for Kp? Well, in this example, I want you to give the expression of Kp, I want you to sub in the numbers for the partial pressures, and then I want you to calculate a value for Kp as well as its units as well. Pause the video, have a go, resume once you're ready to go over the answers. So yeah, looking at this one then, I'm going to start off with my Kp expression. I'm going to have Kp being equal to, and then it's going to be the partial pressure of PCl3 to start off, times by the partial pressure of Cl2 on its own, divided by, and then it's going to be the partial pressure of PCl5. Now the next thing I'm going to do is sub in my numbers, so I end up with 263 for PCl3 times by 263 for of course chlorine as well, divide it by, and then it's going to be 188 itself. Now I'll put that in my calculator, and what I actually end up with is a value of 368. What about the units? Well, in terms of the units, I've got kilopascals as my units for partial pressures, so of course I'm going to have Kpa times Kpa at the top. There's my products, divided by, and then it's going to be Kpa on its own. These two cancel, and I'm left with Kpa on its own there, and there's my units and my value for Kp itself. Now moving on, what about if we weren't given these values in terms of our partial pressures to work out Kp? What could we do instead? Well, the first thing is we need to be able to work out the number of moles of substances we've got in our reaction mixture at equilibrium. And of course, we might need to be able to use a rice box to do that, which we've looked at in a previous video. But of course, we work out our number of moles of each of our substances at equilibrium. And then what we can actually find is something called a mole fraction. And the mole fraction is basically saying what fraction of the total moles is going to be of that particular reactant or product. Now let's say if I'm dealing with the following reaction over here, where I've got A, and that's in equilibrium with, of course, B. It's a reversible reaction you can see over here. And at equilibrium, we were to find out that in our container we've got 3 moles of, and then in this case we're going to go with A to start off, and then we've got 7 moles of, and then we'll go with B. If I were to look at this, right, the total number of moles in this case is going to be equal to, and then we would say 3 added to 7, and that's going to be equal to 10. Now if I were to find the mole fraction, I would use this equation over here, where to work out the mole fraction, I would take the number of moles of the substance I've got, which in this case is going to be A, and I would divide by the total number of moles. Now if I were to do that, right, in this case, I would have, of course, to start off with the number of moles of A being 3, the total number of moles being 10, and to work out the mole fraction of A, I would just do 3 divided by 10, that gives me 0.3. Now in terms of B, right, to work out the mole fraction of B, what would I do? Well, I've got 7 moles of B, I've got 10 moles in total. 7 divided by 10, that gives me 0.7 itself. Now in terms of this, we know that of course our mole fractions over here is going to show us what fraction is going to be, of course, A, and what fraction is going to be B. And one rule that we need to be able to establish is that the total of these two numbers of 0.3 and 0.7 of all of our molar fractions added together, it's always going to be equal to 1. So I know, of course, that number is going to be right of 0.3 and 0.7. It's likely to be right based on that information. So yeah, what's the next thing that I can do? Well, if we were to look at our partial pressures, let's say if I were to have a total pressure, and that total pressure of this actual vessel was going to be 100, and then we'll go with atmospheres, which is a very, very high pressure. If I were to look at this, what does this actually mean, this total pressure? Well, it's the total pressure taking into account, of course, A and B. It's the pressure that they actually exert themselves as a whole. So yeah, if we were to look at the mole fractions, right, the mole fraction, if I were to times that by the total pressure, I can actually get my individual partial pressures. So to find the partial pressure of A in this case, what I would do is I'll take my mole fraction of 0.3 times that by the total pressure of 100. I end up with 30, and it's going to be, of course, atmospheres in this case for the partial pressure of A. To work out the partial pressure of B, same type of thing again. I'm going to take 0.7, my mole fraction, times by the total pressure, and I end up with 70 atmospheres in this case. And so what you can see is I've got my individual partial pressures and my individual mole fractions as well. Now another rule is that if we were to look at the partial pressure, we know that's going to be the pressure exerted by one of the gases in the mixture. But if we were to look at the total pressure, that's the pressure exerted by all of the gases in the mixture. Now what does that actually mean? Well, it means that our partial pressures, if we were to add them up, we should end up with a number of 100 atmospheres in total. And of course, this number will depend upon what is your total pressure and the units of it as well. Now moving on, if you were to look at an example, in this case you need to give the expression for Kp, find all of your mole fractions, find all your values for partial pressures, and then work out the value by subbing into the expression a value for Kp and then its units as well. Pause the video, have a go, resume once you're ready to go over the answers. So yeah, let's say if we were to look at this, we've got 2 lots of A, 2 lots of B react together to form 3 lots of C. In terms of this, we're told at equilibrium, we've got 1 mole of gas A, 2 moles of gas B, and 3 moles of gas C. Because it's told us the equilibrium moles, we don't actually need to use a rice box over here. We're also told the total pressure is going to be equal to 500 kilopascals, and we need to find a value for Kp using this information. Now the first thing is that I'm going to do is I'm going to work out the total moles that I've actually got to begin with, and that's going to be equal to 1 added to 2 added to, and then it's going to be 3, and that's going to give us 6 moles in total. Now, if I were to work that out, of course, that's normally going to contribute to 1 mark with our mole fractions or with some other information as well. We need to get that down every time. Now, the next thing that I need to be able to do is find the mole fractions of A, B, and C. So A is going to be equal to 1 divided by the total number of moles, which is going to be 6. 1 divided by 6 gives me 0.167, and that's going to be rounded as much as possible. And of course, we can try and keep our numbers in our calculator and then round at the end, but of course, I've got too many numbers in this case. If I were to look at B, the mole fraction of B, that's going to be equal to 2 divided by 6, and that's going to give me a value of 0.333, and that's going to be reoccurring, of course. And then if I were to look at C, right, that's going to be equal to 3 divided by 6, and that's just going to be equal to 0.5 itself. Now, of course, I can check if these are going to be right, but adding them all up, they should equal 1, but I'm going to leave it as it is for now. Now, the next thing is I'm going to find the partial pressure of A, and that's going to be equal to the mole fraction of 0.167 times by the total pressure, which is going to be 500 kilopascals, and that leaves me with 83.5, and it's going to be kPa. If I were to find the partial pressure of B, I do the same thing again. It's 0.333, or I could just do 1/3, and that's going to be times by 500, and that leaves me with a number of 166.5, and that's going to be kilopascals as well. And then the partial pressure of C, that's going to be equal to 0.5 times by 500, and that gives me a value of 250 kilopascals. Now that that's done, right, we've done the bulk of this, we now need to give the Kp expression, where Kp is going to be equal to the partial pressure of C, and that's going to be, of course, to the power of 3, divided by the partial pressure of A to the power of 2, and the partial pressure of B to the power of 2 as well. So, of course, we sub in our numbers now, where we end up with 250, and that's going to be cubed, divided by, and it's going to be 83.5 squared times by, and 166.5 squared as well. So we put that in our calculator, and we end up with a value that's going to be 0.0808, 3 significant figures, and then our units in this case is going to be kilopascals to the -1 itself. The reason why is because we've got 3 lots of kilopascals at the top, and then we've got 4 lots at the bottom. They all cancel, we're left with 1 over kilopascals, and then of course we move it to the top to get kilopascals to the -1 itself, and there's that one done as well. So moving on then, last question for you to try. Pause the video, have a go, resume once you're ready to go over the answers. So yeah, we've got a similar type of thing over here again, where you can see, of course, I've got 2 lots of NO2, make an N2O4. We're told we've got a seal flask, it's heated to a constant temperature, and it's allowed to reach equilibrium. And the equilibrium mixture, so we don't need a rice box again, contains 5.4 moles of NO2, 0.3 moles of N2O4, and the total pressure in this case is going to be 5 atmospheres. We need to find Kp, and we need to give our answer to 3 significant figures as well. Now, the first thing that I'm going to do is I'm going to work out the total number of moles. So the total moles in this case is going to be equal to, and it's going to be 5.4 added to 0.3, and that's going to give us a number of 5.7. Once that's done, I can find my mole fractions of NO2, which is of course going to be equal to 5.4 divided by 5.7, and that gives me a number of 0.947. Once that's done, I can find the mole fraction of N2O4, and that's going to be equal to, it's going to be of course our value of 0.3 divided by 5.7, and that's going to be equal to our value of 0.0526 itself. And there's our first part done in terms of the total moles and the mole fraction. What about the partial pressures? Well, the partial pressure of NO2 is going to be equal to 0.947, and that's going to be times by our atmospheres of 5 in this case, and that gives us a number of 4.735. And then if you were to look at that, the units is still going to be atmospheres. If I were to find the partial pressure of the next thing, which is N2O4, that's going to be equal to, and it's going to be of course 0.0526 times by 5 again. We end up with a value that's going to be 0.263 itself. Now, of course, that's going to be atmospheres too. The next thing is I need to find a value for Kp, so I'll give the expression. We've got the partial pressure of N2O4, and that's going to be divided by the partial pressure of NO2, and that's going to be, of course, squared. Sub in my numbers, I end up with, of course, my product, which is going to be 0.263, and that's going to be divided by 4.735, and that's going to be squared. That gives us a value of 1.17, and that's going to be times by 10 to the power of -2. In terms of my units, I end up with atmospheres, and it's going to be to the power of -1 itself. And there's that question done there.